Hello everyone. In this lecture we see heat transfer from finned surfaces. The mode of heat transfer between the solid surface and the adjacent fluid medium that is in motion is convection heat transfer. The convection heat transfer is governed by Newton's law of cooling and which is given by convection heat transfer rate is equals to HA delta T. Here H is convection heat transfer coefficient, A is heat transfer surface area, Ts is surface temperature and T infinite is surrounding fluid temperature. And if you want to increase convection heat transfer rate, here we are having three choices. That is increasing convection heat transfer coefficient or increasing heat transfer surface area or increasing the temperature difference. So in many cases the surface temperature and fluid temperature are kept constant by design considerations. So we may not be able to increase the temperature difference. And the next choice for increasing convection heat transfer rate is convection heat transfer coefficient. So increasing convection heat transfer coefficient may require installation of pumps or blowers or increasing the existing capacity of the pumps or blowers. In many cases it may not be also feasible. So the alternative that presents for increasing the convection heat transfer rate is increasing the heat transfer surface area. So heat transfer surface area can be increased by attaching the surfaces to the heat transfer surface area, and these attaching surfaces are called as extended surfaces or fins. Here you can see the typical fin that are being used in a two-wheeler cylinder head. And next we see typical application areas of fins. The first one is radiators for automobile. You might have seen the radiators in cars or any four-wheeler vehicles, and cylinder heads of scooters and motorcycle, air compressors and electrical motors. So you can see them in this diagram. And next we see analysis of fins. So the important assumptions that are taken in the analysis of fins are: the first one is one dimensional heat transfer along the fin length, which means the temperature gradient exists only along the fin length, which means dt by dx exists and dt by dy and dt by dz equals to 0. And second assumption is steady operations, which means the properties are not going to change with time, which means dr by dt equals to 0, and with no heat generation in the fin, which means there is no internal heat generation within the fins, which means volumetric heat generation is equals to 0. And the third assumption is thermal conductivity of the material to remain constant, which means thermal conductivity is not a function of temperature. And the next assumption is convection heat transfer coefficient to be constant and uniform over the entire surface of the fin. So even though the convection heat transfer coefficient is a strong function of fluid motion, for the simplicity of the analysis we are considering it as a constant and uniform over the entire surface. So for the analysis of fin, we consider a rectangular fin whose length equals to L and width equals to B. And now we take a volume element at location X whose length is equals to delta X and cross sectional area as AC and perimeter is P. So which are all kept constant, which means cross sectional area is constant, perimeter is constant, the length of the volume element delta X is also constant. Now consider this volume element. There is a heat conduction to the element at location X, and there is a heat conduction from the element at X plus delta X, and there is a heat convection from the volume element. Now under steady state condition we can write energy balance on this volume element as rate of heat conduction into the element at X equals to rate of heat conduction from the element at X plus delta X plus rate of heat convection from the element, and which can be written in the expressions as Q dot conductions at X equals to Q dot conduction at X plus delta X plus Q dot convection. And to find out the conduction heat transfer rate at length X plus delta X, we can make use of Taylor series. So Q dot conduction at X plus delta X is equals to Q dot conduction at X plus dq dot divided by dx into delta X by 1 factorial plus d square dq divided by dx square into delta X square by 2 factorial and so on. And here we will neglect the higher order terms and we will consider only up to first order differential. So the value of q dot conduction at x plus delta x is q dot conduction at x plus dq by dx into delta x. And q dot conduction is given is conduction heat transfer, which is governed by Fourier's law of conduction and which is given by minus ka into dt by dx. And q dot convection is convection heat transfer rate, which is governed by Newton's law of cooling and which is given by ha delta t. Here area is surface area, which is given by perimeter times length of the volume element. Now we substitute q dot conduction at x plus delta x in equation 1. So what we get is q dot conduction at x equals to q dot conduction at x plus dq dot by dx into delta x plus q dot convection. Here we can say on both the sides we are having q dot conduction at x, so we can cancel it out. And now we can substitute q dot convection as hp into delta x into t minus t infinite. Here we can see on both the expressions we are having delta x, so we can cancel delta x also, and we can substitute q dot conduction as minus ka into dt by dx. And now we multiply both the expressions by minus and we will be getting d by dx of ka into dt by dx minus hp into t minus t infinite equals to 0. And in the assumption itself we took that thermal conductivity, cross sectional area and perimeter to be a constant, and so we can take k and ac out of the differentials and we will be having kac into d square t by dx square minus hp into t minus t infinite equals to 0. And now we divide both the expressions by kac, we will be getting d square t by dx square minus hp by kac into t minus t infinite equals to 0. And now we can write d square t by dx square as d square of t minus t infinite divided by dx square, since t infinite is a constant value which is surrounding fluid temperature. And now we can replace this excess temperature t minus t infinite into another parameter called theta, which is a temperature excess. And now we'll be having d square theta by dx square minus hp by kac into theta equals to 0. And now we introduce one more parameter called fin parameter, which is m, which is equals to root over hp by ka. And now we can replace this hp by ka into m square, and finally we will be having d square theta by dx square minus m square theta equals to 0. So which is the required differential governing equation for the heat transfer through fin, and this is a second order linear homogeneous differential equation. Since it is a second order differential equation, we need two different boundary conditions for solving this second order differential equations.